All right, welcome back everyone. My name is Jibril Ben-Sidrin. I'm hosting this webinar on behalf of CESA Systems. Today's guest speaker is Professor Mark Rogers, who will tell us about how to develop Ishikawa diagrams and make continuous improvement decisions when you have limited data. The actual title is a lot more technical, but I'll let him explain that. Mark comes with a management background plus very strong academic background. He's a professor at Rutgers Business School in supply chain management. He teaches and has developed courses on demand planning and fulfillment, operations management, operations research. Prior to that, he held management and strategy positions at Bristol Myers Squibb, the Port Authority of New York and New Jersey, ZS Associates, Verizon. So very diverse background in terms of industries, which is pretty rare, I think, from pharma to transportation, consulting, telecommunication, and both public and private organizations or government related, I guess, and private companies and publicly traded. So very excited to have him with us today. He holds a Six Sigma Black Belt, a doctorate in industrial and systems engineering, 2 master's degrees in engineering. So thank you so much for being with us today, Mark. Mark will tell us about the key challenges in root cause analysis, what we can learn using Ishikawa diagrams, reminders on probabilities and Bayesian networks, then some guidelines on how to develop models when you have limited data. And he will illustrate that with some examples and a case study. We will have time for Q&A at the end. Just a few words about our sponsor today, CESA Systems. As many of you know, CESA is a world leader in lean enterprise with a catalog of 2,500 products, now actually more than 14,000, 15,000 plus client companies worldwide, including many of the Fortune 1000. You recognize some of them here on the screen, but also thousands of mid-sized companies. And the products they use include training games, office furniture, lean office, ergonomic office, workshop furniture, including workbenches, computer protection, TPM type of stations, quality control, etc. In the logistics area, gravity flow racks, trolleys, electrical trolleys, Kanban system, Heijunka systems, floor markings and safety signage, as well as in the Industry 4.0 space, wireless and-on lights, digital screens, digital KPI management software, and also the still very important traditional visual management with magnetic whiteboards and accessories. Without further ado, I will pass it on to you. Mark, thank you so much for being with us.
So good afternoon, everyone. I hope you all can see my screen. But, you know, just kind of based on the title, I know the title has a lot of technical terms in it and a lot of things that, you know, the terms might be new to a lot of folks, but really this work allows us to use tools like fishbone diagrams, which we may have seen before, that give us some learnings and apply those types of qualitative learnings in a quantitative setting with the help of advanced statistics and statistical inference of things like that. So this is really just a framework to kind of support, you know, problems of this class. And this is actually part of a paper, an academic paper that was published in the TQM journal. I have a link here at the bottom of the slides here. And if you're interested, I can share that with you offline. But my just to kind of add some color to this, you know, growing up, you know, I've always kind of been a math and science nerd. And, you know, if you can't tell from the pictures, I was a geeky kid. But I also had a love for basketball as well. And then the X's and O's kind of really helped me allow me to use the math and to make decisions. And that kind of brought me to college, where I went at Rutgers University, where I studied material science engineering, and I also met my wife there as well. As you can tell, these are the early 2000s, where style at that point wasn't particularly great. So bear with me. But early in my career, after leaving Rutgers, I spent some time, as Jabril had mentioned, at Bristol Myers Squibb, and also earned a master's in pharmaceutical engineering. And this is really my first exposure to process improvement in Six Sigma. And this work really kind of germinated from my experiences there, having worked in a clinical pharmaceutical supply chain, where oftentimes you're operating in a constant state of disruption with limited process knowledge, and really kind of helped me shape my work, at least this particular work, on a project of this type where you have limited data. From that experience, I decided to move on to graduate school, where I got my PhD in industrial engineering and also dual master's degrees in industrial engineering and statistics, and held various management roles, consulting roles, analytics roles, as Jabril had alluded to, and finished my PhD in 2016, which is almost 4 years ago now, and joined the faculty at the Rutgers Business School in the fall of 2017. So coming up on 3 years, actually almost, yeah, will be the beginning of my 4th year in September, which goes by very quickly. So wish me luck as part of the tenure process, but just wanted to share a little bit of color about my career and kind of how that trajectory worked for me. So I wanted to start this discussion with a polling question for the audience. And really what I wanted to know is, we've all been charged with improving a process of some sort. But for those of you who've been charged with improving a process with limited data, what was your course of action, or what would be your course of action? Would you A, seek out proxy data, so data that's from a similar process if you have it? B, wait till the process matures. So if it's a brand new process, wait till it matures to collect more data. C, push back to leadership. Or D, which unfortunately I've had to do in my professional career sometimes, is just to wing it and rely on intuition. So Jabril, maybe you can help me with this and see what the audience thinks here, but I'd be interested to see what the group thinks, and hopefully we can get some feedback.
Yes, so you should all be seeing on your screen right now a quick poll with the same questions that Mark mentioned. You can go ahead and enter your responses. We'll try to get to at least 60% response rate, if not more. Just so methodological disclosure, we are 76. We have 76 people on the call right now. So that just to give you a sense of the statistical representation, I guess.
Sure.
Actually, and we have more people joining. Actually, right now we're close to 80 people.
Okay. Well, in the meantime, what we could do is I can go to the next slide, and we can come back to the poll question once we kind of have more data, if that's okay.
Sure.
Okay.
Well, actually, I think I have to. 75% have voted, and so the numbers are back now. 63% will seek out proxy data. That's really the 64%. So that's really the large majority, and then 15% wait until process matures. 15% just wing it, and very few push back to leadership. So we'll close this one.
So thank you all for your feedback. I'll just try to address some of the feedback I got from the audience. So I think, if proxy data is available, that's obviously the best course of action. But I'm sure that you've all been in the situation where you have a unique process, where you may have some proxy data to serve as a surrogate, but it may not address all the nuances. So you still have to kind of find a way around that. The second part too, also waiting until a process matures to collect more data, that's a very rational solution, and I think that's also a reasonable course of action. But in certain instances, you may be under pressure from management if there are quick turnaround times or rapid response times to make process improvements with limited data, and waiting for a process to mature, it could pose some risk. And just winging it, again, that's kind of a symptom of what I had previously mentioned, where you just kind of have to go with your gut in some instances and rely on intuition. But what we'll do, I mean, pushing back to leadership, the final point there, which got the least votes, oftentimes isn't feasible because of time constraints and resource constraints, things of that nature. So, really my points that this research and this work kind of hones in on answers A, B, and D, kind of relying on data and also relying on your gut to kind of bridge that gap of process maturity or lack of data. So to just add more, the next slide here, to add more color to this, I mean, obviously we kind of talked about some of these key challenges. We all been in situations or where you may, or maybe not all of us, but where you've been pulled from your day-to-day responsibilities to participate in data collection efforts for another process or another project, for a process improvement project. Also, you may be, overseeing or managing a process where there's a low frequency / high risk of events occurring. So you don't really have a lot of data or poor data quality, or it's a newly introduced product. So this really helps to kind of shape the question of how we can proceed when we experience challenges of this type. So, this is pretty critical here when we kind of proceed through the DMAIC cycle, particularly the analyze phase, where we kind of identify and validate select root causes of a problem. So root cause analysis is critical here in the analyze phase, and it's very challenging to proceed through this analysis phase if you don't have data and don't have information, or may have limited information. So, a lot of these, I'm just listing out some of the analyze phase activities. What you see kind of highlighted there with the red dotted circles there are the activities that really rely on data. Exploratory data analysis, regression, hypothesis testing, trend lines, bar charts, graphs, things like that really allow us to have insight into information based on data. But one of the commonly used tools at this stage also is an Ishikawa diagram or a fishbone diagram, which kind of helps to address some of those qualitative insights as well. And it's a really good tool. And as part of this work, we're going to leverage these fishbone diagrams to help bridge that gap in the event that we have limited data. So what I'm showing here on this slide here is an Ishikawa diagram or a fishbone diagram. And for those of you who are unfamiliar with a fishbone diagram, what you'll see here at the head of the fish here, where you see that this is just an example, you have iron in product. So that's the key issue you're looking to address. And what you're looking for is causes as to why you'd have iron in your product. And you'll see that these large ribs of the fish have different categories or clusters of different issues. For instance, your materials, maybe a big cause of why you're having iron in your product could be due to your raw materials. And as you see, we kind of see there's like a hierarchical structure for each of these little ribs. There's like a substructure there where you kind of drill down a little further until you really can't get any further. So at the very end of, I guess, that tree that you see there, you'll have these critical, what I'm calling critical X's or key root causes that are helpful in explaining why you're having iron in the product. And this information is useful, especially if you do have data. You can bump those up against a regression analysis and see what you're finding and see if those outcomes are true. But how can we use this information to move to the improve phase where we're generating solutions? That's what we're looking to address. So as part of this approach, it's really a three-step approach with sub-steps, of course. But the first step as part of this process is to construct a causal diagram from an Ishikawa diagram, so a causal network. So I'll talk a little bit more about that, but really we're going to take that fishbone diagram and translate it into a causal network, which will show. We're going to work with subject matter experts to do this, process experts. The next step is to approximate the probability of the problem occurring. So that head of the fish, we'll use that fishbone diagram and the causal network that results from it. What we'll build is a Bayesian belief network, and I'll talk about a little bit about that, and we'll use what a method called probabilistic elicitation to help better understand the probability of occurrence for some of these key root causes in relation to the problem under investigation. So once we have that model working, we can use that in step 3 to identify some vulnerabilities. Here we can simulate with it. and identify some critical root causes as a result that will allow us to transition to the improve phase. But our main contribution here is really in step 2 to help bridge that gap here. So there's some key managerial themes. There's a lot of it, kind of, me being an academic, I showed some academic citations there, but just kind of this overlaps with 3 key areas of management themes. So risk management, obviously, continuous improvement, which is what we're talking about, and also Bayesian networks, or probabilistic, statistical inference, that thing. So we're kind of combining elements of all 3 to help develop this framework. So we're going to take a step out of the weeds, because I know I've mentioned quite a few terms that might seem foreign to some of you, but we're going to get into a little bit more into some of the nitty-gritty of Bayesian belief networks and probabilistic elicitation. This will help shed some light and lay some of the groundwork for what's to come. So just think back to probability. This is just going to be a brief refresher. Just some basic concepts of probability. All probabilities are between 0 and 1. Things that are necessarily true, so statements or propositions that are necessarily true, or true 100% of the time, have a probability of 1. And oppositely, things that are necessarily false or necessarily false propositions have a probability of 0. And I want to introduce this concept of exclusivity here. And you can see on the far right, I kind of have some illustrations here to kind of help you understand that. You have 2 events here, A and B. And the term of exclusivity is important, and it's critical here in some instances. So for instance, the first bubble here, the first diagram here, if we wanted to figure out the probability of A and B, it's really the intersection here that's shown in this dotted line, the circle here where A and B kind of overlap. That's the probability of both A and B occurring. So if they're not mutually exclusive, it's just the product of those 2 probabilities if you had that information. However, if you want to compute the probability of A or B occurring, it would really be the area of this entire region here, right, of all A and all B. But because A and B overlap, you'd have to remove that intersection there. So you'd have to delete off or subtract off the probability of A and B, which we computed before. Now, this doesn't account for independence, which we're not going to talk about that today. But if they are mutually exclusive, if events A and B are mutually exclusive, the probability of A or B occurring is just the sum of those 2 probabilities independently. And obviously the probability of A and B occurring together, which would be the probability of A and B, that would be equal to 0. But I just wanted to kind of, give you guys a brief refresher before we kind of jump into a little bit more things. I may use those terms subsequently. So really just, this is all, a lot of this framework depends on or is built off of Bayes' rule, which is a theorem built by a probabilist a long time ago, whose last name is Bayes, and it allows us to compute the conditional probability. So you'll see in the equation up the top here, the probability of event B, and that vertical line there means given. The probability of B given A is equivalent to the probability of A given B times the probability of B over the probability of A. And there's a long proof to get to that, which I won't show. But there's also the law of total probability, which goes into effect here. The probability of B alone is the probability of B given A times the probability of A. Or it would be the sum of all those events that overlap with B as well. We could talk about that, but that's really just kind of a simple explanation there. And if A and B are independent, so if B is independent of A, the probability of B given A is just equal to the probability of B, which makes sense because A would have no influence on the event B. So I just kind of wanted to I may use these terms subsequently in the slides and in this talk. So before jumping into the weeds, I just figured I'd give you a brief refresher. And if you have questions, we can talk about them offline, or I can address them if they come up. So a brief word about probability distributions. So I'm using the weather as a simple example to kind of illustrate this. But imagine you have 4 weather outcomes. It could be sunny, it can be rainy, cloudy, or it could snow. The sum of the probabilities here in the second column, the probability of the outcome, they all add to 1. So the sum of the probabilities of of an entire, I guess, outcome space should add to 1. The sum of all probabilities should add to 1. That's just a simple, illustration there. And there's also this concept of joint probabilities, where you kind of have 2 variables acting in conjunction with one another. And in this case, I'm going to show a simple example down below here, this table, where you have a production backlog and a machine failure. And the production backlog could exist in 2 states, yes or no. You could have a backlog or not, and the machine could fail, yes or no. But if I wanted to know, and this could be based off of data, the probability that there is a production backlog given that there's a machine failure, it's this upper left quadrant here, right? And vice versa, I can kind of compute the joint probabilities or determine them from this table. This is called a conditional probability table, or also a joint probability table sometimes as well, showing that these, and you'll see this again in our models. But again, I just wanted to introduce you to some of the terminology so that you see this, and so that we're all on the same page when we talk about future slides. So this is Bayes' rule again. So one of the things I wanted to illustrate, so obviously they're governed by, the Bayesian networks are governed by Bayes' rule. There is a causal structure, hence the conditional probabilities. You'll see interconnected nodes, which are variables, and then states, which are classifications. So if we refer back to the previous problem, a production backlog would be a variable, and the state would be yes or no. So what you'll see in a causal network, there are these directed acyclical links. Basically, you can go from start to finish and not circle back, and I'll show you how that looks visually. And you can compute the joint distribution, which is critical for us in producing and understanding the results. So here's a simple example that I'll show you where you have let's say that there's a breakdown. You have these nodes here. Each of these nodes are variables, and each of these nodes exists in 2 states here, true or false. And as you can see here, this is a causal representation or a causal network where you have the breakdown here and the emergency feed into the alarm. And as a result of the alarm, 2 outcomes are Mary calls or John will call. And we can work through a series of events knowing that we have this relationship between these variables. And here I kind of have parent nodes and child nodes showing the hierarchical structure. We can talk about that offline. But let's say we have data on this process. Let's say this is a very mature process, and I know the data. I can compute these probabilities going through the table. I can compute these conditional probability tables here. So for instance, we know whether there's a breakdown, there's a probability of 0.001 or 0.999, true or false. And similarly, we can compute that same probability from our data for an emergency, if that occurring as well. I'll draw your attention here to the alarm section here, where you can see here the alarm variable A can exist in 2 states, but it's conditional upon what happens above, whether there's a breakdown or an emergency, those states there. And you'll see here, this table accounts for all different combinations here. There's 4 different combinations of nodes B and E together. And if we had the data, we can compute these probabilities here in this table. And similarly, we can do a similar exercise for nodes M and J by computing this, for developing these tables if we have the data. Now, if I wanted to determine the probability of a specific sequence of events, so the probability, for instance, for this example, that John and Mary call when the alarm goes off while no burglary or earthquake occur, from the tables, I can just basically develop using this expression here, which is the product of the conditional probabilities here. I can determine mathematically, and the formulas are less important, but I can determine mathematically what that exact probability is, which is great for us if we're looking to make a decision based on that. So here it's a very small probability, 0.062%, but the key takeaway here is if I have the data, I can compute that information. But let's say we don't have data. So one of the ways we can bridge this gap is through probabilistic elicitation. So I'm sure maybe some of you have been in focus groups, and they may make you, for instance, rate your, if you're in a food focus group, they make you rate your preference for a certain food item on a scale of 1 to 5 or 1 to 10. This has a similar interpretation. On a scale from 0 to 100, being in percentages, and each kind of these, along this kind of left-hand side of this axis here, these probabilities correspond to a verbal connotation. So if I say, for instance, something is expected, that correlates to a probability of 50 to 75%. And this is a scale that's commonly used in academia and also in industry as well, but it allows us to then, if we do have limited data and I wanted to rely on expert judgment, this allows us to then take that information and convert it to a numerical range of values. So this is useful in quantitative exercises. So again, back to our example, originally we had, just kind of populating this, that we had, numerical values in here, but instead of those numerical values, now we have these ranges here. So instead of numerical values, you kind of have this verbal connotation here, using this elicitation scale. And if I wanted to really recompute this probability now, let's say I don't have data, but I have this information from the ranges, this now translates to a range of outcomes. So that probability that John and Mary call when the alarm goes off, when there's no burglary or no earthquake occurring, it's still very small, but the range could range from 0 to 11.25%. So, this information is still helpful if you didn't have any information prior to this or any data. You could use this to then inform future decisions about your operations in this case. So we're going to illustrate this framework with a case study, again, kind of going from step 1, 2, and 3. So I just kind of wanted to reintroduce the framework. We construct the Ishikawa diagram and a causal network in step 1. Step 2, apply the Bayesian Belief Network probabilistic approximation method in step 2, and then we'll use that to simulate. So I'll work through a case study, which is the one we actually worked through in an academic exercise for this paper. This is actually, the case study we're going to discuss here, which we discussed in the paper, is actually one from an academic journal where they were really taking a deep dive into why they experience long queues at the bank here. And I'm sure you can imagine that we've all been in a situation, not necessarily now because of the pandemic, but where you've had a long line at a bank or at a grocery store, or we can make the translation to a machine backlog, or any root cause, any main issue where we could develop a Ishikawa diagram. But for the sake of purposes, you'll see this long queues at the bank example. And what I'm showing here is kind of a truncated version. You don't see all of the kind of the substructure and the trees. I'm just kind of showing you the ends of each of those fish bones, which result in the critical X's, so to speak, or root causes that they identified. So we're going to use this kind of as a proof of concept for the time being to illustrate this process. So, So the first thing that we want to do, obviously, is identify those key root causes from the Ishikawa diagram. So here's where we're going to, in this particular element or particular phase of this process, we're really collaborating with the subject matter experts to build a causal network. And in this particular case, we've identified the key root causes, which would be step 1. Step 2 now is to remove duplicates and to sort these ideas into groups. Sometimes you may have encountered this where some root causes of certain items may overlap into 2 categories. So for instance, you may have a root cause that exists in the process arm and also the staff arm, which is quite possible. So we wanted to account for that. So we're going to remove the duplicates and classify these into groups. And step 3 is just a simple, a simple step is creating group headers or names for these groups. So we usually group these by likeness or similarness. And oftentimes you may have heard this process referred to as affinitization, where you kind of cluster like variables or like themes into an overall category. Right? So we just give these names. So this is a critical part. This allows us to then really kind of stay organized throughout this process. And helps us to keep track of things as we move to the improve phase. So you'll see here in this particular example, my co-author and I, we actually clustered these root causes into, let's see, 4 different themes here. And we gave each of those root causes a node ID just for our own bookkeeping purposes. And you'll see the final outcome node here, which is Q length. That's the variable we're looking to understand. That's I guess the big Y, right? And what's happening here, what you'll see is that also for each of these nodes or variables, we've defined 2 states. So these are existent binary states. And I put an asterisk next to what we're calling the undesirable state. So for instance, for node P1, capturing daily demand information, this exists in a present or an absent state. The absent state is the undesirable state because if you don't have that data on the daily demand information, that can create issues downstream. So we went through that sort of logic, kind of very intuitive in this case. And usually 2 states, a binary state, set of states works really well for problems like this. But I'll transition here, and obviously the outcome node, the undesirable state is an increase in Q length and not a decrease. So we want to make sure that we're understanding why the Q length was increasing. And if there's a decrease in Q length, that will be helpful also. But we'll know what nodes are critical and what variables are critical to an increase in Q length as a result of these exercises. Now, the next stage here, what you'll see here is actually a causal diagram. My co-author and I actually built this ourselves, but using the taxonomy from the previous slide, we went through this qualitative exercise of kind of linking systematically which nodes influence one another, and ultimately leading to this outcome node that you'll see here in red, node 01. So when we've done this, just for this exercise, my co-author and I did this as just an academic exercise. She and I did this together. But if you were working with subject matter experts, usually it's something where you kind of have, I've done this with sticky notes with subject matter experts working together where they kind of can build that out kind of in real time, and there's kind of consensus amongst the group. And it's actually a fun exercise, but since this kind of is a smaller exercise, I think this is a better one to share with the group for today. But if you're interested in others, I can share some others with you offline. But here you'll notice that, for a given node like M3, we have at most 2 parent nodes, P1 and P2, P1 and M2 feeding into it. And you go from, for instance, left to right here, and that's the only direction you can really go. You can't follow this diagram and go back to where you started. So that's the acyclical portion of this network, which is what I alluded to previously. Now, when we create our Bayesian belief network, a critical element of this is, using conditional probability tables. And, it's a tedious exercise that we had to go through. And I'm using S3 here as an example, which is this node here in orange, where the parent nodes S4 and S1, both of which exist in 2 states, we have to work through this this conditional probability table and populate that, and using this probabilistic elicitation scale here, which I've called out more explicitly here on this slide. But this allows us to kind of work through this systematically and do some simulations in the future. But we have to do this conditional probability table for each node in the system, and the table will look very differently. And ultimately, the result will be something that looks like this, where you kind of have ranges. So, for example, I'll look at node S3 here, and these 2 particular combinations. For instance, the probability that S3 is present given that S4 and S1 are absent and present respectively, that is improbable. And as I mentioned before, the complement to that probability, since all probabilities add to 1, if you just sum down the column, the complement to the improbable would be probable based on on that scale, the probabilistic elicitation scale. So, the transition across this table, sometimes, it's difficult to agree on consensus, but it's a painstaking exercise that allows us to, then once you have the completed table, to simulate and do further analyses. Okay. So this is just the baseline output of the model here based on our data inputs. Again, as proof of concept, and our response variables here at the end. The probability that O1 increases is about 56%. So that's our baseline. We're gonna, in our heads, measure everything against the baseline, and we can use this network as a tool to simulate or run several experimental trials. Since we have ranges of probabilities for each of those variables, we can kind of pick ranges and run through realizations using this model. So how do we do this? So what we did in our case was we executed 60 random trials, which are very quick to do. Each node has two states, obviously an undesirable state and a desirable state. And we did a regression analysis on the output. The output being the probability the Q length increases given a certain set of experiments. And the output of the regression allows us to identify critical nodes. I won't get into the details of this since, for the sake of time, a regression study can be, kind of detailed to explain, but I can talk about that offline if you have questions. But as a result of this regression analysis, we identify key variables which would inform the solution generation before stage, which is critical to the improve phase. So here's an example of a simple experimental trial. So for instance, the way you would interpret this is we have evidence that suggested that M3 was in the absent state. So for instance, that was with probability 1. We know that M3 was in the absent state. M1 was in the unfavorable state, and P2 was also present. So we know for sure that those events occurred. The probability that O1 increases, again, is about 62.5%, which is different from our baseline, which we would expect. But, as you can see here, there's various iterations here that we can execute with turning different nodes on and off. We chose 60 for this particular example, but you could run as many trials as you want because it's very quick to do in this particular tool, which is called Open Markov, which is a free simulation tool that's open sourced and publicly available. So I'm going to transition to the solution generation stage. So what the paper had identified as some of their solutions that they had identified were what you see here on the left-hand side: boosting incentives, promotional activities, automated teller, web banking solutions, so on and so forth. But what we found is that these variables, these nodes of interest here, actually they showed as significant variables in the regression. So what we had demonstrated here, and I think this is a critical slide for us, and also for proof of concept work, and it was a sanity check for us, is that our analysis tied back to actually what was implemented in practice. And we found a lot of the variables here synced up more or less to what was found through their full DMAIC lifecycle efforts, which was great for us. So this allowed us to really see how we can use this method as a surrogate in the event that you don't have data. So I'm going to pause here. We have another polling question, Jabril. So my question to you all is, obviously understanding variable relationships is quite challenging. So what other tools do you commonly use to understand or assess variable relationships? So we have a few here: design of experiments, hypothesis testing, machine learning, correlation analyses, and maybe something else. But I just wanted to get a feel from the audience, how you understand or really take a deep dive into relationships between variables, at a high level. So I'll pause here.
All right, you should also be seeing a quick poll on your screen.
Okay, so we'll give folks a couple minutes.
Yeah, approximately 50% voted. If we get to 70, 80% again, that'd be great. Getting close or above 70%. Anyone else? A couple more votes. Okay, perfect. We're very close to 80%. And 40% design of experiments, 30% correlation analysis, and then hypothesis testing, 25. So machine learning actually 2%. So I guess that's very limited. And something else 5%.
Okay. So I'll start with the machine learning aspect. I think one of the biggest pitfalls with machine learning is, in a sense, that you kind of have to treat it like a design of experiments, right? Oftentimes we don't have understanding of what's kind of under the hood of an AI algorithm, and it's kind of difficult to assess causality. I actually have another research project where we try to match up based on historical management cases which analytical tool works best. And one of the pitfalls of AI and machine learning is that it doesn't work well in cases where you need to have a causal understanding. But design of experiments, I think, is a really popular one. If you're able to execute experiments on your production line, that's great. And I think one of the biggest hurdles to doing things like this is really the cost, right, of running an experiment. Sometimes these could be cost prohibitive. What I found in practice is that some version of B or D are, if you have data, are more normal, or what's expected, and B and D are actually very related in some sense. You can throw in regression into that as well, but you could also make the argument that that's part of a hypothesis test also. But usually what we see is B and D, some version of that, and sometimes A if you're able to run experiments. So, but it's good to see what the audience is, talking about here. Something else, I'm sure there are various methods to, understand causal relationships. Again, a lot of it may rely on your prior knowledge, but these are good discussions. So thank you all for contributing. Let me see here. Whoops. Okay. So I'm just going to wrap up here. So really the next steps here and conclusions is that what we've kind of demonstrated is that this framework can really serve as a surrogate in the absence of data, and essentially enables a smooth transition to the improved phase through our proof of concept studies. Now, some potential extensions here that we're actually working on as we speak are, really collaborating with the subject matter experts to make this model a live model, for instance. So if this is a new process, you may have a working Bayesian Belief Network model, but as you gain more subject matter expertise and more knowledge or more process expertise, you can enhance your BBN, you can modify it and maybe change up the structure a little bit, and even populate some of those probabilities with real data if you have it. Also, one of the other extensions is actually applying simulation-based optimization methods, which are more advanced solutions, really to prioritize proposed solutions that come out of this. So this is a more rigorous, those of you who are operations research or optimization folks, you can apply these models kind of as a black box optimization tool, and maybe it can be used in conjunction with machine learning and AI as well. But these are things that we're kind of working through now or in the early stages of developing. And with that said, thank you all for listening to this talk. I've got my contact information here. If you want to take a look at some of my other work, I've got my personal website here and my LinkedIn page. But at this point, I just wanted to thank you all. And if you have questions for me, we'll reserve some time for that. So thank you all for listening.
Great, thank you so much, Mark. Excellent. Like I warned you all, this is going to be a rather technical presentation. Well, they're all technical, but in a different way than we used to. And we do have a couple of initial questions. The first one is related to the choice of the method. Why and when would you use this method rather than maybe wait for more data or choose another way of analyzing?
Yeah, so I think, I'll use this example as kind of a reason why. I guess it's kind of kind of illustrating this method. So, if you think about a common area where these models are used is airline risk safety. So if you think about a plane crash, plane crashes in theory are low frequency. They don't happen very often, but the risk is very high. It's a severe, right? So it's a huge impact. So really taking apart, there may not be a lot of data for a particular class of planes or aircrafts. These methods are used quite often in this space, where you have low frequency, high risk events that you're trying to improve upon. So that's one area where these are very, very useful and have been used in the past. I think I have a colleague who worked with the FAA who's deployed these types of models in this space. So that's one area. And I think the other instances, new processes that are mission critical. And I think particularly this might be illustrated with the COVID-19 crisis, where you have rapid turnaround and high risk of, in the event that you're not unable to satisfy demand. You may have seen lots of cases where for hand sanitizer, for example, companies have been bringing these, changing over their lines to produce hand sanitizer. There's lots of risk associated with that if you don't have that expertise. So models like this can help you quickly simulate and, get to solutions. And again, if you're able to iteratively revisit this, you can ultimately start to proceed along the DMAIC cycle. So I hope that answers the question.
Another question related to actually the first Paul question about the option for none of the above. The participant said that in his case, he would try to better understand the current process to identify augmentation potential.
Yeah. So, sorry, can you repeat the question, Jerome?
Yes, I guess. What about none of the above? What about other ways to address this situation? It's similar along the same lines of the same this question. I guess it's a follow-on to that initial one.
Oh, sure. So I think there are numerous ways to kind of approach this. I think I'll just kind of highlight some qualitative ways. I think focus groups that kind of get to like the qualitative market research groups types of methods. Those types of tools are often, you'll see kind of on the marketing side being used, and they have some promise in this area as well. But since we're kind of in the continuous improvement phase, or continuous improvement space, I should say, I think making data-driven decisions is critical here, and qualitative efforts alone, just like maybe surveys, for instance, that they can lead to some insight about a process if that process is simple and not particularly complex, or if you want to obtain some high-level takeaways about a product or about a process. I think that's helpful, but really this is geared towards kind of making data-driven decisions. So I'm sure that there's a wide range of qualitative tools out there, and maybe even machine learning if you have presumably if you have similar data or proxy data, that would be great. But in nuanced cases, again, low frequency, high risk events or quick turnaround times with new processes, this is something that can really serve as a surrogate to get to the improved phase.
Another question regarding the just wing it. Could you? Yeah. It's going with your gut feeling, I guess. But could you consider that as collecting more data, or training your gut in a sense, just being able to deal with these small signals that you're able to process, not necessarily as formally, but you may be also using these kinds of models in a more informal manner to try to put some structure around dealing with limited and informal data.
Absolutely. So I think that the just wing it, that was kind of my way of, I don't want to make light of those types of situations, but that really speaks to the essence of relying on maybe your prior knowledge or your own intuition, making your own judgments based on your experiences. So in this particular model, yeah, I mean there are various managerial structures that are out there. I think a lot of times too, people may apply, loosely apply managerial, things like the theory of constraints or information theory in some aspects where you have limited information, trying to make a judgment. But what I meant by just wing it was really just relying on your gut. But in this case, if you think about kind of the way we build the BBNs, we are kind of applying some of that same knowledge here, but we're using it in a very structured way to produce, a tangible quantitative output, which then allows us to make decisions. So that's really kind of what I was alluding to with the just wing it aspect there. But there are various managerial strategies out there. Theory of constraints could be used as one, but that can be applied qualitatively. But it runs the gamut. So.
A question regarding the application of these methods in the energy system. Do they apply similarly in any sector? Would you need some adaptation, I guess, perhaps based on the nature of the decisions, the nature of the data that you're gathering? Is this across sectors, or how would you envision perhaps applications specific to an energy company? This person is in a solar, for example, interested in the solar and green building sector.
Okay, so I actually have quite a few papers in the energy space, so this kind of hits near and dear. So, I've seen, models of this type that are used in the energy sector to understand outages, right, and why they failed. Kind of a fault tree type of aspect there. In the energy sector, since it's, you have tons of data. So the whole belief aspect of the Bayesian Belief Network relies on, using that probabilistic elicitation and that Likert scale, so to speak, that I'll deem it that. But in an energy sector, you have this interconnected system that you could view kind of as a causal chain or a causal network or a fault tree or some sort of network with nodes and arcs. And presumably you have lots of data. You have demand data, you have outage data, you have consumption data, you have generation data. So you could use this in a probabilistic way to really understand why an outage occurred. I have a colleague of mine who actually, he and I did our PhDs together, that does kind of something in this space, more in the reliability engineering space. So that's really kind of where I see the biggest application of this jumping out to me on the energy space. But if you're interested, whoever that asked that question, I'd be happy to talk about that offline. But that's a great question. It's definitely generalizable when you think about systems, interconnected systems. So
we're beyond the time, but we still have many participants still. So last question regards the subject matter experts. So it's kind of a comment / question, I guess. The ability of the SMEs to provide guidance or provide direction.
Sure.
How do you work with the SMEs? Could you elaborate a little more on how do you get that type of direction or insights?
Yeah, so I think a lot of it is, I'll speak to my experience on this with a similar project in the clinical pharmaceutical space.
Yeah, and if you may, just to interrupt, so sorry about that, but just as to add, how do you also avoid perhaps that risk? Because it's, in a sense, it's positive and could be a double-edged sword. A subject matter expert guides you in perhaps a biased direction. So, sorry.
Yeah, sure. No. These are great questions, and these are certainly things that we've experienced. So one of the things that when we embark on these efforts, we have usually, I'll speak to one project, but a major pharmaceutical company where the company designated these a set of individuals as subject matter experts for a particular process, and with those subject matter experts, we kind of had to, a colleague and myself had to work to, one, introduce the concepts of probability to them, in a more detailed way than I did today, but kind of had to lay out a day's worth of work where we can go from, root cause identification all the way through to Bayesian Belief Network development and understanding how the model behaves. So we kind of QC'd everything together. But I think one of the challenges is oftentimes you have dominant personalities in the room, or you may have somebody who doesn't like to speak up, or maybe they just communicate in different ways. So I think what has helped me is actually a tool that I've seen done in continuous improvement projects called multi-voting, where you kind of have post-it notes so you don't have voices drowned out, and you can reach a consensus, and that kind of helps. There's various other tools to kind of help reach that consensus. I didn't touch on them today for the sake of argument, and we didn't talk about them in the paper as well. But those are things that are very important. And actually, there's a lot of literature, particularly in that probabilistic elicitation space, that talk about really, I think it's psychology literature that talk about how to move, how to achieve consensus with making decisions with having other folks, a lot of potentially conflicting opinions involved. So it is a challenge, and there's lots of academic literature on that, and also probably managerial literature on that. But I found multi-voting to work really well. But it really depends on the cast of characters and such. So I may have to dig back in the toolbox if it occurs again. But multi-voting seemed to work well for me.
Great. All right. Thank you so much, Mark. Very, very more than informative, insightful. Great tool. I will just conclude with a few words about the context of this presentation today. It is part of the CISA Systems Academy, which is both a physical lab space where we host hundreds of executives who come and talk about methods, and also specifically, of course, as far as we're concerned, the tools that can help them implement this. As you see here, one example, which is a large whiteboard, and our founder actually was here designing an Ishikawa diagram for our own purposes. So good illustration here. And for those interested, also, we do provide a number of different catalogs. It's a great resource, 2,500 products at your fingertips, including all those that you can see here, but really many more. If you'd like one, feel free to request one, PDF or paper, or schedule a session to review. This is more in terms of the tools that help you in your daily work. And again, if you wish to contact Professor Mark Rogers, you have his contact information here and his email. You also have mine. I guess you'll receive emails from me. Also, I really would like to invite you to join our LinkedIn group. If you go to LinkedIn right now and add /groups/8605-844, you will land on this group, and that's where we share our webinars, both the announcements and the recordings. Also, I invite you to share questions if you have any questions, anything that you think will be of added value. It's a non-spam group. We are trying to really be careful. So great way for you to stay connected with while still being in control of the information that you get. That's it for today. Oh, one more thing. The certificate, Professional Development Hour certificate, will be sent to those who request it. Just send an email. We will receive actually an assessment by email. If you don't receive it, please feel free to email me. The assessment is a brief few questions just to document that you were on the webinar or on the recording, and then we'll send you your certificate. Thanks again, Mark. This was really excellent. Thank you all. I look forward to seeing you in a future webinar.
Thanks, Jibril. Thanks, everyone.
Thank you.